Okay, so this is a long topic or long talk title, but basically I'm going to talk about the ULPMs and what happens if they're in a binary neutron star merger as well. So the motivation is that we have periodic FRBs and the periods are 16 days and probably 150 days, and potential explanations are some binary system, shrouding, or precession or rotation. So I'll advocate for this long period scenario. So let's talk about the challenges for the other models. Precession generally requires very young sources, and this is sort of, I think, challenged from, say, the offset distribution for, say, the periodic FRB R3. The significant changes in polarization you should see in the precession scenario. You should also see an underlying fast periodicity, which people don't find. And since it's related to age, you should see many more FRBs with much longer periods. And so an activity may anti-correlate with period. Binary scenario, the frequency evolution is actually opposite of what's seen. So this is almost, I think, ruled out, at least a very simple model. So you can have a more complicated binary scenario, but I guess it's just a more complex model. And of course, you'd also have DM changes with phase and other things that are unobserved in the binary scenario. So it's getting less favored. The source density, so the R3 is rare. Something like R3 is rare. So the rarity could favor something exotic, like a very long period source. So, but there are also long period sources, as we heard, in our galaxy. So let me just go through one example here that is sort of not well known in the radio community. It's this CCO in RCW103. It has a 6-hour period. It had millisecond duration bursts, similar to a magnetar. And it has long-term outbursts, and it also has non-thermal hard X-ray emission like a magnetar. So it has all the features of a magnetar, something you'd call a magnetar, except the P dot, because its period is so long. So, and so I think this is pretty secure now as some sort of ultra-long period magnetar. It's radio quiet as far as we know. And there's this galactic burper, the 77-minute thing, which has a very high brightness temperature. Then the gleam source that Karshkev talked about a bit, that also has a very high brightness temperature. We can largely rule out a white dwarf just based on energetics and source densities and things like that. Then there's the Meerkat source that Karshkev talked about, very close by, 300 parsecs. So that implies that many more exist. So how do you spin down a magnetar to very long periods? Like there's lots of different models. You could have a fallback disk. You could have enhanced spin down from monopolar winds, opening of magnetic flux during outbursts. You could have giant kicks and giant flares. You could form intrinsically a very slow magnetar, or you could have all of these operating. So some of the implications. So let me just talk about the source density. So this is doing some Monte Carlo population synthesis, similar to this paper with Vicky Kasky. Basically, birth neutron stars in the galaxy, see how they evolve and how they propagate into galactic potential. And when you do this, this is showing their age versus the rate of formation, and the core collapse rate is plotted here. So based on the distance, this is this color scale here is the distance to the source. Based on the distance, you can sort of derive a minimum age for them not to exceed the core collapse rate. So this implies that these objects are sort of old. So strictly lower age limits, just based on the distance. From the X-rays or non-existence of X-rays here, you can also put an age limit of, say, 1 million years or so for these objects. Then based on the age limits, you can get the source density based on the core collapse rate, which is this 10 to the 5, normalized to our galaxy. And you can see that the RCW103, the SGR, the XDINs, and this long period object here all sort of lie on the same sort of line. So that means that they're compatible with being a significant fraction or even comparable to the core collapse rate in formation. So they should be very common. And there may be a tentative, I don't know, I would claim anything here that maybe the longer period ones are rarer. And as Karshdev talked about, there's a significant bias against detecting these. So this is showing the same plot he did. If you do the horizon for an imaging survey like SKA or DSA 2000, your horizon is about a few kiloparsecs, which means that you'd expect about 100 detections in the next decade or so. With this conservative assumption, of course, if we're already finding more now, then this is very conservative. It's probably a lot more than 100. So E-Rosita will also probably detect about 100 extins. And based on the source density here, about 10 of these could be these ULPMs. So E-Rosita will detect 100 ULPMs. Okay, so these will require follow-up, and the horizon is limited to about 4 kiloparsecs based on the galactic MH. And StarX, which is a proposed NASA mid-X, could potentially be useful for this. So now let me just go to current radio emission. Andre will talk about this, I think, later this afternoon, but you basically need magnetic pair cascades as a necessary condition for radio emission. And you can sort of have a primary paraluminosity from these pair cascades. This is the energy in the primaries, and the radio is some small fraction of this primary paraluminosity. The formula for that is this. And so you have some efficiency from to radio from pairs. You have some charge density required by transient conditions. You have a gap height, which is some microphysics scale. And you have an area of the flux tube where things are active, and that's the speed of light here. So for curvature pair gap, it's like this paraluminosity goes as the voltage, or E dot to the -1/2. So how do you go from pulsar to an FRB? And so you increase the area and you increase the charge. Both must increase. And so there's really only two options. You can oscillate or shake a magnetar, which is Andrea and I's model from 2019. This likely works. Or you can physically move a neutron star fast, like in a neutron star prior to coalescence in a binary neutron star merger. And so both of these things could make FRBs. Okay. So this is a little paper I had earlier this year with student Alex Cooper, who's now at Oxford. So it's pre-merger emission in binary neutron star. There's different models. There's reconnection, resonant cross-reactive shattering, wind-driven, and there's pulsar revival, which is this work. So you basically have an unmagnetized neutron star and a magnetized neutron star, and then merging. And because of the motion of the magnetized component, you have large electric fields that are generated, that are and that must be screened, that demands pair production. And so is there any realistic prospect for a magnetar to be involved in a VNS merger? And it really depends on the delay time distribution and the field decay. Now that we know that these ULPMs or ULPPs exist, we know the field decay time for these objects is probably much longer than is typically assumed. So it could be 10 million years before the field decay. So it's possible they could be a component in, if you can form one. There's this paper that recently came out that has a magnetar in a circular system that will eventually, based on evolutionary models, produce a double neutron star system. So that's also very interesting. So okay, the setup is magnetar or neutron star and an unmagnetized primary, and the details of the current emission are in this efficiency parameter. And so when you do that, the time to merger and the flux density, for different magnetic fields, you can see the time to merger is a few seconds before merger is when the radio emission have significant flux density for 100 megaparsec merger, sensitivity, detection before merger for some 1 milliJASK sensitivity is tens of seconds. This is sort of the fluence in the last 3 milliseconds, and you can see you can constrain the efficiency or the magnetic field and of the component as it merges. And so the rate estimate. So you can scale the rate as the efficiency times the magnetic field cubed. In this case, depends on if the scaling of the radio luminosity goes to the Poynting flux or the voltage, times the intrinsic rate of binary neutron star mergers. And so you don't expect any in chime or maybe even cord, but you could see some in SK DSA 2000, say a few events per year. And so how do you observe this? You have to observe a short gamma ray burst, or you have to get lucky and see a binary neutron star merger in your field of view, right? But of course, you're helped by the dispersive delay. Okay, the other aspect here is that the horizon distance in the radio is much larger than LIGO, Virgo, Kagra. So you could potentially detect this radio emission much further out than the gravitational wave detectors. So the question is, how do you get this radio emission prior to merger? And I think the best way to do that is to take short GRBs that have very fast alerts in the future and point your radio telescope either in software or very fast in hardware and wait for the dispersed radio signal prior to merger to get to you. So that's basically, hopefully radio observers can do this in the next decade.
So in the table of 2 slides back with the SKA mid number, for example, there it says SKA AA mid. Huh?
Yeah, it's I don't know exactly what it is. It's
yeah, I know what it is. So it's an aperture array, and you have to digitally move.
Okay,
that's what you want.
Okay,
but that's going to be a while.
Okay, I mean that's
not the SKA that you think. This is the next one.
Okay, but so maybe build that.
Yeah. I shall bring a big check, and I will not fill in the number. You sign it. We have an aperture array currently in the world. It's low far. Yeah. So it's not your 800 megahertz in the frequency formula equation you gave, but it can repoint.
Yeah.
In practice, it's not instantaneous in practice, but very quickly.
Right. So I guess in the future, there is a plan for very fast alerts within, say, 50 milliseconds or so from space for GRBs to the ground, and then hopefully you can.
Yeah, well, you have a minute of dispersive delay down to low far, so it's perfect.
Yeah.
Unless, well, of course, they have to emit at that frequency.
Any other questions?
But I wonder how you estimated radio emission.
So we have the efficiency here. We don't. It's limited by this formula here, right? So this is the maximum, and then you have something eta less than 1. So we just have. We don't know, right?
How much is eta?
10 to the for radio pulsars, it's 10 to the minus 3-ish to 1. If you get close to the depth line, it's close to 1. Goes as the voltage. So
So it's just